Sorry. So April 21st, that's again a Tuesday, and I believe it's Talent Elementary. But we were looking for volunteers, and typically the time is like 2:30-ish to 4, so with cleanup. But of course that's during lab, but if you needed to switch labs, if you wanted to volunteer, that would be, of course, okay. They already have the experiment planned, so the theme is space exploration that week. And so the club was thinking about doing, you guys remember the Alka-Seltzer lab. So that's a fun one to do with the Niños, right? They start screaming, Alka-Seltzer. And then they also wanted to do the liquid nitrogen ice cream to kind of connect it to, Artemis 2. And obviously they use liquid hydrogen and oxygen. And since we're not going to haul around liquid hydrogen and oxygen, liquid nitrogen is much friendlier. And then, of course, always a good excuse to make some ice cream. So if you want to help with that, I would love at least like 1 or 2 people to help. Or, if you really can't make it Tuesday, we could always use another hand, maybe on Thursday. Oh, sweet. All right, so we at least have 1 volunteer to hold down the fort. And yeah, so they might have a meeting on Friday, a club meeting, but you don't really have to go to that. You really just have to show up to this. And again, we can brief you guys. So yeah, if 1 other person, you could always try to rope Matt back into it. No pressure. No. But yeah, it's really fun though, and not that that's why you should do things, but it gives you something to write about when you're trying to talk about all these applications and what a wonderful community member you are. Well, that's a great place to talk about that. Oh, and then other exciting announcements. So super excited. So we actually have official approval now. And I meant to change the syllabus, and then I guess I didn't hit the save button, so it didn't change. So I will actually fix the syllabus today, but we're going to be shifting the syllabus around. So May 12th, it is official now. So I'll shore up the times and everything, but we are at least approved for our field trip to the Oregon Caves. And so again, it is far. I thought they said officially it was 2 hours, 45 minutes. I don't remember. Despite having driven out there, I totally forgot how long it took. But it is quite a drive. So just start planning that. And if you have work or something, right, see if you can get off. So start making arrangements. I would love everyone to go. So it'd be lots of fun. And then we'll also shift some stuff around. Like I said, I meant to actually have the syllabus shifted, but I can at least kind of go over orally what's going to change, because there's other kind of exciting things happening. So yeah, let's just check in where we're at. So week 4 is going to stay the same. So we'll still do our electrolysis lab. And then I plan to leave this as is, so we'll still have a buffer week. And I think there's a few people still missing the first lab, so that could happen this week. And then week 6, I think the new plan, so I'm waiting to confirm this. So they want to do a photo shoot, RCC marketing. They want to come get action shots of y'all. And so what I think I'm going to do is probably move this 1-pot reaction to week 6, assuming that they'll come out and film that week. So probably on the Tuesday, but I'm also waiting for confirmation for them. But at least the 1-pot is like kind of more doing stuff and like, woo, color changing. So I figured that could be some cool action shots. And we may do like other demos or something to try to look extra exciting. But yeah, I didn't want to show this lab because this lab is pretty boring. It's not like boring, but it looks boring. Like, oh, we're just collecting stuff off a detector for radioactivity. Although there's some cool parts, but again, for photo shoot excitingness. So this will move because this will be 1-pot. This will be field trip. And then we won't have lab on Thursday, right? We'll just have class, and we won't have a quiz that week. And then this will probably be radioactivity, so just shifting everything around. And then probably keep that as our aspirin lab. And then, of course, reserving this for the posters. So I'm hoping next week to actually hand back feedback so you can work on your posters and papers and all those good things. Oh, that being said, so while I'm thinking about it, the poster requirements are on Blackboard already. If I could pull up Blackboard. So if you look, you could start poking around with these poster examples. And you can look at these sample posters. And so I like the poster requirements. And so I still have, so remember Dr. Murphy is actually a chemist, as much as he wants to deny it. But so I still left Dr. Murphy's old paper on here as an example. The only drawback about this is it's a PDF, so you can't edit this. But my poster on here, this old relic, so this is an example of my poster that I presented at ACS, but you can download it, and then it's a PowerPoint format, and so you can kind of see how the poster thing works, and so you can use this template, right, delete all this stuff, make your own boxes or whatever, and kind of start designing your poster or kind of playing with it. So that's already there for you. And then other ideas of posters. So next time you're in lab, I don't know if you've ever like really paid attention to that poster that sits above the aquariums. So that was from a former student here that did like a conference or research experience over the summer. But that just gives you like another idea of kind of how to do the poster, right? You got your title, your name, introduction, and then a big scheme of like what's going on, other relevant kind of pictures. So just so you can at least kind of start thinking about that. I feel like this spring quarter always flies. All right. Oh, and then yes, sorry. The last thing I forgot is, of course, since we got field trip approval, yay, we also have to sign our life away, of course. So just confirm with me, I guess, by doing the paper. Well, is everybody like planning on going or not going or like? Okay, so most people are yes. So probably like email me if you're not going, just so I have like a short list. But I definitely need papers back too, so that also confirms that you're going. So I need, again, your life signed away. And then I think I have one minor student. So I think you need your parent's signature. I don't know if there's more of you. So yeah, just get everything signed and returned to me ASAP, because I also have to just make sure this paperwork is all approved by everybody. And I just want a list ASAP of who's going. And then, like I said, if you want mom to go, brother, sister, significant other, let me know ASAP, because we do have to have that officially approved. But so sooner rather than later, or any sort of thing like that. And then again, there will be an alternative assignment if you cannot go. We'll be very sad and miss you guys, but again, I totally understand with work and driving over there. But try to carpool if transportation is the issue. So you guys can start coordinating amongst yourself, carpooling and all those good things if you need. All right, and then, so everybody got 2 forms. So if you're not in class today, make sure you get these, because again, I need you to sign your life away. And I can also email these out if anybody wants them emailed. All right. Well, Yeah, so that does bring us to a good point. So there's no like budget, unfortunately, to like print posters officially. So what I've recommended in the past is that once you have your PowerPoint, right, there's a special way to print it where it tiles it, and then you can take your paper printouts and then paste them to either like a trifold or a regular poster board. So that's kind of what we've done in the past, since, like I said, there's no department budget, unfortunately, to do printing. They won't let us use their in-house printers. At least I've inquired in the past, and they've always said no. And then it costs, I mean, I don't know what it costs today. The last I checked, like usually it's like 30 to 50 to do it at like Staples or something. And I really don't expect people to pay that. So again, usually what people do is at the end, I have a bunch of people emailing me their PowerPoints, and I can help print them if necessary, right? Because I can send them to the first floor color printer, and then you can just tape them together. I mean, I'd probably rather that you print it just so that it looks more professional. Yeah, because we want to at least kind of somewhat look somewhat professional, but again, I'm not trying to like knock people for not having access to supplies, but yeah, that's still like my best recommendation is do it on PowerPoint, so that way you can always email it to me and I can print it for you, and then you can tape it on there. And that's my best low cost, no cost method. But yeah, I mean, if you want to spend the extra money and like get it professionally printed, like I've had people do that in the past, and they brought in like professionally printed posters, but I'm not expecting that. Okay, so let's start off with this one. So let's just see if you can warm up with this. Oops, sorry, what did I do? So yeah, start with 31 here. I just wanted to scoot this down here. There we go. So we have our equilibrium constant for this dissociation, right? Our solubility product constant is 1.8 times 10 to the negative 10 at 25 degrees Celsius. So it asks us to calculate our delta G at 25 degrees Celsius. And then is it possible to prepare a solution that is 1 molar in both of those? So how would you approach it? So take a few minutes to just try it out for yourself first before we go over it together. So do we find our formula too? So remember, your book does have this useful page of equations. And then it's just picking the correct one, right? Using it. So which one is relevant for this one? Bless you. Yeah, so right, we're just looking for any equation, right? So kind of going back to our problem, we have K, they want G. So that's our equation here, right? So any K equilibrium. So we've looked at lots of equilibrium scenarios. Uh, this is the one just from the back of the book. So chapter 23. I don't really have like a standard cheat sheet thing, but yeah, I would probably use your periodic table for that. And if people need like new copies for that, or, depending, I don't know how people like to study. But that's kind of like my recommendation is like have your equation, maybe have a sample problem on how to use the equation so you kind of know what you're looking for. So yeah, so let's plug that in then. And then just looking at our units, so R 8.314. So joules Kelvin, so that looks good. Temperature we need to convert to Kelvin, so 298. And if you already plug this in, you guys can let me know what you got. Oh, 8.3. So just punching it in now. So I see chat answers. So they got, looks like the same thing I got in here. So 5,592 joules. Oh, skipped a 5. And so then, is it possible to prepare our solution that is 1 molar? And so we could probably best to re-plug it into our formula, although if you kind of remember from yesterday's example what's going to happen, right? So we had found, we did the same process, not yesterday, but Tuesday, and then, right, plugging it into our Q, because it was asking the same thing, so we can take our ratio, so we'll get this ratio, right, Q over K. So it should be not spontaneous, but again, let's just plug it in so we're all on the same page formally. So then we want to use, right, our comparison. And so again, right, that sign gets eliminated now since we're doing a ratio essentially. So we'll take our Q snapshot over our KC. And again, just kind of verify. And so what does the positive value of delta G mean? Excellent. So not spontaneous. And it's always good to like repeat that a million times because it is kind of odd. It's like, okay, we're looking for our negative number to be spontaneous. And then again, let's just plug this in to get our ratio. So KSP, it's asking us to make a 1 molar solution. And again, 1-to-1 dissociation, just making sure we're all squared on that. And so obviously that would be 1. I'm just trying to go through it quickly, but not too quickly. You can always like slow me down. I always assume that like people are like bored and like totally way ahead of me. I'm like, yeah. I get overexcited as well. So 8.314, plugging it in, 298. So that our Q is 1 over our K value. And so it should spit out our same number, but again, we'll just plug it in to be all on the same page. Oh, sorry, I forgot my natural log of that. And so yes, this is going to come out. So again, just verifying, and it was 1, so it gives us that same number that we had just calculated. But yes, we cannot make that solution, which kind of goes back to this point, right? It's not spontaneous. And so making this high molarity solution already doesn't sound good, right, of moving in the forward direction. And so then we say, no, can't make 1 molar solution. So not under these conditions currently. All right, and that's the end of that question there. All right, questions about that one? All right, so now try this one here. And so kind of 2 parts to this, right? First, we have to remember just how to calculate our change in enthalpy of our reaction. And then, right, this is just saying use our standard values. So if you don't have your book handy, that's fine. You can always pull up another standard sheet. So you could pull up this one. You could also just like Google standard entropy chart, and you should get a bunch of standard tables. So see if you can find some values. We can always go over the values that people find. So yeah, first step, find our change in enthalpy of our reaction, and then we want to figure out our new Kp at 400. So I'll give you guys a few minutes to start it. And then, of course, make sure you're looking at everything in the gas state. So at least just kind of start sketching it out, but y'all keep going independently. And you can vaguely remember, right, the standard heat of formation for elemental things should be 0, but you could still look it up. But remember, anything in its elemental form is 0. So do we get this for our change of enthalpy of our reaction there? And just double check my numbers and everything. Could be small discrepancies. So were we all okay with finding our change in enthalpy of our reaction? Do we all remember how to do that, right? We just find our values. So I found negative 374.9 for PCl5, and then negative 287, and then just take products minus reactants. They were all in a coefficient of 1, otherwise, right, we would have had to multiply it. So do we all get this at least? And then, so what formula do we want to use then? So, okay, then it says given that our Kp is 0.55 bar at 250 Celsius, so what's our Kp at 400 Celsius? So what equation is good for that? It's probably one of those ones at the end there. Kind of look at what you're given too, right? Because you have bar, so what's that? So which Yep. So yeah, we want to use this one. And again, they're basically the same, right? It's just one, we're looking, I mean, it's all about our change in enthalpy of our reaction. So yeah, basically our same format. So we want to pick our 2-point Clapeyron-Clausius equation, or Clausius-Clapeyron. I'm usually used to it being the other way. And so yeah, our 2-point form, again, right, our hint, okay, we have 1 point, we want to add another point, we have our delta H, so now we can plug that in. And then units shouldn't matter on the pressure because it's a ratio, so we're just trying to find it in our bar units then, that's fine. So I'll just keep sketching it out while you guys do it as well. And again, just make sure you're pairing. So I'll make my low temperature K1 and then, right, make sure you don't flip-flop anything funny. So I'll rewrite my equation for a second. And trying to find my KP. And we have it at 0.55 bar. Found. And then, of course, don't forget we have to convert this to joules, right? Because of this R value is in joule land. So then this has to be in joule land. And then T2, I didn't do my Kelvin conversion, so let me do that. Bless you. So we have, looks like 523. And I probably could do mental math, but that's okay. And 673. And T1 is lower. So again, just making sure that that all works out with my placement so you don't get a funky sign or something. All right, so now we just have to plug everything in. So right, let's just solve for this so we can get a number, and then we can take everything to the E and get rid of that natural log. So I'll just punch everything in for now. Well, our temperature difference, 150 still. So I'll try to take a shortcut. Oops. So then I have this so far. Again, just double check me that I punched everything in correctly. It gives us negative 4.506 or so. So we all get to this part, right? And then from here, just take everything to the E, so that goes away, giving us our ratio, and then we'll have to get a number. So E to this answer, so then I get 0.01104. So just algebra. So times 0.555 to get rid of it on both sides. So then I get our new pressure of 0.006 bar. Questions about that one? So again, that's just finding our new equilibrium constant, right, based off of pressure at this temperature, so it looks more unfavorable. Any questions on it? Speak now. All right, let's do another. So this one's maybe a little easier. So now this one is just saying give us the signs. So what's the sign of each one of these processes? We have 3 examples. And so figure out first, right, is this an exothermic, endothermic process? And then are we increasing or decreasing entropy? So take a few minutes to try to look at those. So let's look at A together. So what type of a reaction is this one? Come on, guys. Got your hints right there. Yeah, combustion reaction, right? Kabloomy. Combustion. All right, so then combustion reaction, what happens? What's our change in enthalpy? What do we know? Yeah. Oh, someone's trying to, we don't need numbers for this. That's the whole point of this exercise, is you shouldn't need numbers. I mean, you could knock yourself out, but the point is combustion, kablammy, exothermic. You know that, right? It makes heat. Yeah, exactly. Like, we can speak from personal experience. We can burn some stuff in lab. Yeah, so we expect it to be exothermic, so good, negative. And then what about our entropy though? So this one could be a little tricky, right? Compare your mole count. So what did you find with the entropy? How many moles do we have on this side? Oh, because you can't say 6, 7, because then yeah, but yeah. Well, anyways, I'm not totally up with a 6, 7 joke or 7, 6, but yeah. So you go from 7 to 6, so then that's decreasing, right? So then what does that do to your entropy? Positive or negative? Yeah, lower it, right? Because there's less potential microstates, just from having, again, less moles. Excellent. So those are signs for the first one. All right, what about B here? So CO2 looks like sublimation process, dry ice. Excellent. So enthalpy positive, right? We have to put heat, and then state change. Good, positive. Did everybody catch that? Makes sense. So, right, for our entropy, obviously you're going from an ordered form to gas everywhere. So again, way more microstates. And then what about this last one? This could have been a little tricky for the enthalpy, but what's our enthalpy? Is there heat exchange? So they're just mixing. Is that typically a process that involves heat exchange? Uh, What do we expect? We open a stopcock, right? Does anything happen heat-wise if they're the same temperature? Yeah, no, right? So change in enthalpy is 0 for this process. So it's only entropically driven. And then, so what happens to our entropy as things mix, of course? So then increasing entropy there. So again, any sort of mixing thing. All right, that was pretty good there. Any other thoughts, questions on this one? All right, I'll let you look at 71 now. This is a good one, since it has that little star. So allegedly it's a little trickier, but this is, some real world data here. So we're measuring the solubility of potassium iodide as a function of temperature, and it's given in grams per liter. And so now, right, think about this. What can we do? So we want to determine our value of delta H for our reaction from this data. So I'll let you kind of think for a second. And So what equations are relevant, and then what else do we have to do, or probably need to slightly calculate something. So kind of given a hint here. So what do we do for this one? We're kind of looking at two equations, right? I've kind of like sketched this out because we have to, of course, take into account our disassociation, right? We are in grams per liter, right? So like technically maybe we should think about converting this to molar solubility, right? But at the same time, so what form of our equation are we going to use once we get past this solubility bit? Especially because we're given a bunch of data, right? Yeah, right. Van Hoff. That's always like I feel like these are like your real world applications. Like anytime you're in lab too, right? You're gonna be picking 2 points. And so yeah, we want to use our Van Hoff. And I'm gonna be slightly lazy then and kind of prove a point too. But we can ignore the fact that we need to do a conversion to molarity, right? Because we're doing a ratio anyway. So that molar mass is going to cancel out. I just wanted to point it out so we don't like forget to do it later. But there, right, it's going to cancel out. And so the part that we just need to account for is, of course, getting our relationship between our solubility and KSP. So I just sketched it out because like I was telling you, I don't remember the formula, but I just sketch it out. So again, 2 equivalents of iodine to give us our KSP of 4s cubed there. And so then we can just pick 2 points from our data. And I just picked the most extreme points to get us, I don't know, what I felt were the best points. You could literally pick any 2 data points, right? Any of them should work or give you close to a value. And then again, just make sure you sanity check yourself of which one you're assigning as the K1 and T1. And so I just picked the higher value for my own sanity. So I'm just calling this one my K2 and T2. And then, of course, right, converting to Kelvin. And so this is T1, K1. So I don't know how far we made it or didn't make it. So then now we're getting to this point where we could start sketching out our 2-point formula here. Well, I don't know why I keep writing the constant all crazy. And so I'll just plug in our S for this value. Well, actually our 4's kind of go away. So I'll take it, so natural log 0.366 cubed over, so I just divided the 4s already, over 0.058 cubed. So again, I just kind of, I already just got rid of that, got rid of the molecular weight thing, blah. So moving on is equal to, so trying to find our delta H of our reaction and verify this data. And then, sorry, let me do my temperature conversions. So we have 283 and don't feel like mental mathing it today. Oops, sorry. So 353. So now just plugging in. Again, making sure we plug in the correct corresponding temperatures, so the higher one. Again, it wouldn't matter if you swapped them. Everything would go out, right, as long as you flipped everything correctly. And so what do we get for our value? So I'm still plugging in numbers. Oh, I feel like I did something wrong. Oh, because I multiplied it instead of dividing it. Sorry. So that was my bad. Times 1 over 8.314. Sorry. The calculator error. There we go. Ah. There we go. So then we should get about 65,000. Well, that's in joules, right? Because of our 8.314. And so then divided by 1,000. And so what does that give you? And so about 65.6 kilojoules. And then that's a pretty good number, right? So then it says the actual value of the delta heat of this reaction is 63.4 kilojoules per mole. So pretty good, right? The experimental data pretty much confirms that. And again, hopefully everybody plugged that in correctly and verified that. All right, if we wanted to do, I know we're kind of like running out of normal official class time, but you could do this one real quick, or I could leave it up there and then just kind of sketch it out for people. But this is just another practicing our Clausius-Clapeyron 2-point form of the equation. So yeah, I'll probably just leave this up here and then I'll sketch out the answer for everybody. But I do want to get people going on the quiz and everything. And so make sure that you keep up on the quizzes, especially I have a lot of people this quarter like Zooming and time conflicts and all that. But I'm missing a lot of chapter 21 quizzes from a lot of people. So I have chapter 21 if people need to do that. So make sure you get that taken care of. Otherwise, I'll hand out 22. So on solubility, I feel like it should be a pretty good quiz. So yeah, I'll kind of hand this out in case people want to start working on that. But then I'll also sketch out this one so you guys can keep practicing if you need. And then again, if you're not in class, make sure you're bugging me for the quiz. I'll lose track of who's where. Oops, sorry. Throwing things. So yeah, keep on top of your quizzes. Thank you. And then I'll try to get back the papers that I do have. I'm still behind on grading labs, so I will do that. Yeah, I'll sketch this out for everybody. But yeah, if you need to take your break, I know we've been going for a while, so I don't want to like super fry everybody's brain. But I'll at least sketch this problem out so you have the answer on the notes. I'll keep the stream running in case people have questions, but then I'll kind of let people solve stuff and ask questions, right? This is again your time. So ask me, ask me, ask me.